Section 26.4, the outer planets. So when the sun formed, as I mentioned earlier, and it turned on, all of the gas in the inner solar system was pushed outwards. And that gas that was pushed outwards made its way to the outer solar system. And over time, just like the rocks and things accreted in the inner solar system to form, the four terrestrial planets, the gases that were left over formed the outer planets. And so what you have are four very large planets that have very low densities. They're mostly just gases collected by gravity. Um, they generally have solid cores, but the surface is not a surface as you would imagine, but instead it is just layers upon layers of gas. All the gaseous planets, the outer planets, are appreciably larger than Earth. Very much so. They're larger than all the inner planets. Um, they're also more spread out than the inner planets. And these planets include, of course, Jupiter, Saturn, Uranus, and Neptune. So the first of the outer planets, and by far the largest planet of all in the solar system, is Jupiter. Jupiter is beyond Mars. It's about 5 AU from the Sun, so about 5 times the distance of the Earth from the Sun. It is 11 times Earth's diameter and about 318 times Earth's mass. It is by far the biggest planet. Its composition is more liquid than gas or solid, and it's cold enough for you to have liquid gases in where Jupiter is, and so that's why you see the surface of Jupiter appears to flow and move and things like that. Because of all those gases, the atmospheric pressure on Jupiter is extremely high, more than 1 million times what you would see on Earth. And that's assuming you could, stand on what would be some surface of Jupiter, which you can't. It's primarily made up of hydrogen and helium, leftover components of star formation, leftover components of what was left in the solar system. It's often said that, Jupiter just needed a little bit more mass and it would have been another star. That's not exactly the case. It's made out of the same stuff in relatively the same proportions, minus the iron core. However, Jupiter would have required a lot more mass for it to become a star. It's made up similarly, but it would have needed a lot more stuff. Again, you don't have a definite surface on Jupiter. What you have on the inside is just a core and then layers and layers of gas. Okay, so if you tried to stand on this, what you would see as the surface of the planet, you would just sink down to the bottom. You wouldn't sink all the way down to the bottom because you'd sink to a point where your densities were equal. But assuming you could sink all the way down to the bottom and stand on this core, um, the temperatures that you experience, daytime and nighttime, would essentially be the same. The sun doesn't make it through all these gases. So the temperatures at any level inside of Jupiter is essentially going to be the same. I do want to point out just the composition here, hydrogen and helium, and these are liquid hydrogen, right? Metallic hydrogen. On the inside, liquid metallic hydrogen. This is just another form of the way that hydrogen forms. And then you have the iron core in the center. Now, not only is Jupiter important because it's the biggest planet, but it's also important because it's one of the easiest ones to see. At night, Jupiter is the fourth brightest object in the sky after the Sun, the Moon, and Venus. So if you spot it, you can spot Jupiter pretty easily. It is generally very high up in the sky compared to Mercury and Venus, which are generally lower. It's generally very bright. If you can get a look at it with a telescope or with some binoculars, you can sometimes see distinctive features like you see in the image of Jupiter here. Additionally, if you look at it with a telescope, you can see Jupiter's 4 largest moons. If I can find the pictures, I'll attach them of pictures that I took of Jupiter through my telescope where you can clearly see the moons with it. It's super, super interesting. Actually, I take it back. My wife took the pictures. So she's good with a microscope. She's good with a telescope. Regardless, you can clearly see the moons. and you could clearly see the moons with a telescope at any time. And that's why in the 16th century, when Galileo was alive, he had a telescope and he was able to see the 4 moons of Jupiter. He observed them moving around Jupiter over and over again. Now, Jupiter has something like 70 moons, but 4 of them are really, really big and easy to see. And these are called the Galilean moons because they were discovered by Galileo. Just a little bit of interesting pieces about each one of these 4 moons. Io is the most volcanically active world in the entire solar system. It resides relatively close to Jupiter, and it is pulled by Jupiter's gravity very often, causing volcano eruptions to occur very, very frequently. Europa is one that we as humans are working to understand more. There's a giant layer of ice over the top of that moon, and below it is liquid water, or is assumed that there might be liquid water, and that liquid water could contain life. And so there's work to go investigate that. Ganymede is the largest moon in the entire solar system. It's bigger than Mercury. And then Callisto is one of the most heavily cratered objects in the solar system, and you can see that all those speckles, those are craters on the surface of the moon. A planet like Jupiter, you would essentially expect it to be hit by a bunch of craters, or by a bunch of random space rocks, because it has so much gravity, it's going to pull a lot of stuff towards it. It's close to the asteroid belt, so it's going to rip asteroids out of the asteroid belt. And as those things are approaching Jupiter, sometimes moons can get in the way. And Callisto just seems to be one that's gotten in the way a bunch of times, and taken the hit for Jupiter, so to speak. Beyond Jupiter is Saturn. Saturn is known for its ring system. If you can ever view this in a telescope, it is one of the most spectacular things you'll see, because the rings are clear and apparent as they are in that picture that you were looking at on this video. Saturn has more than 60 moons, but again, just like Jupiter, many of the moons are not that big. There is one moon of Saturn called Titan that is important, and there'll be another video attached with it that will show you more about Titan. Titan was visited, and you can see it. Saturn is twice as far from Earth as Jupiter is. So Jupiter is at about 5 astronomical units, so 5 times the distance from the Earth to the Sun. Saturn's at about 10. Saturn, if you view it in a telescope, it's much harder to see, but it's also hard to pick out at night compared to stars. But it is, you can still see it with the naked eye, and it is very interesting to see in a telescope. It has the lowest density of all the planets. If you could somehow fill up a bathtub with enough water, Saturn would float. Water has a density of about 1 gram per centimeter cubed. Saturn has a density of somewhere between 0.7 and 0.9 grams per centimeter cubed. So it is less dense than water, and so therefore it would float. Saturn, again, is surrounded by rings. These rings are bits and pieces of rock and ice and dust that were thought to possibly be moons that were ripped apart by Saturn's gravity. The rings also orbit around the planet, much like a moon would. And then finally, Titan, which you see down here at the bottom, is Saturn's largest moon, and it was visited by the Cassini spacecraft, and I will add that video to this week's lectures as well. About twice the distance from Earth to Saturn is Uranus, about 20 astronomical units. Uranus and Neptune are further out than Jupiter and Saturn. So whereas Jupiter and Saturn, you see a lot of liquid gases. As you go further out in the solar system, you start to see more ice particles, frozen gases. So Uranus and Neptune are sometimes called the ice giants, whereas Jupiter and Saturn are sometimes called the gas giants. Uranus and Neptune are significantly smaller than Jupiter and Saturn. Uranus is really interesting because it rotates basically on its side. So the Earth is tilted at 23.5 degrees, right? So we're tilted a little bit as we rotate. Uranus is tilted at 98 degrees. So it is literally laying on its side as it rotates. So it rotates in a direction almost perpendicular to the direction that it revolves. It's thought that this came from an ancient collision years and years ago that caused Uranus to essentially turn on its side. Um, as with all of the Jovian planets or the outer planets, Uranus has a ring system. Jupiter and Neptune also have ring systems. They're just faint, small. You can't see them. They're not at all like Saturn. Saturn's is by far the fanciest one. But those outer planets all do have rings. Saturn's not the only one. And Uranus's atmosphere is mostly made up of methane, and hence this gives it kind of its bluish color. Beyond Uranus is Neptune at about 30 astronomical units. It's about 4 times the size of Earth, but it's significantly smaller than Uranus. The atmosphere is mainly hydrogen and helium, again, but more frozen than liquid. And Neptune's orbit around the sun is highly elliptical. It takes a really long time for Neptune to go all the way around the sun, and it forms a large ellipse. One of the really interesting things about Neptune is when Uranus was discovered, it was noticed based on predictions from Newton's laws that there should have been another object affecting its path. So Uranus was expected, if there was nothing else out there, it was expected to go around the sun or travel in this path in a certain amount of time. But when you observe it, it wasn't doing that. And so what that meant was that there had to be some other mass further out. Using the law of gravity and Kepler's laws, scientists were basically able to predict where Neptune would be. And the day they predicted it, they went outside that night, pointed their telescope at the sky, and immediately found it. Or within an hour, I believe. It was that night that they found it. It did not take very long. It was predicted before it was ever discovered. They knew where it was going to be and knew where to look because of the way that it affected the other planets. Now, beyond Neptune, or at least scattered throughout the solar system, are other smaller objects that we call dwarf planets. Up until 2006, Pluto was still considered to be a planet. But that mainly was just because it was discovered, not shortly after Neptune. But it was discovered at a time when we didn't know about all sorts of other stuff that was out there. So as we started to learn over time of other objects similar to Pluto and in similar regions of Pluto, Pluto essentially got demoted to a group known as dwarf planets. Dwarf planets are sometimes leftovers of planet formation or pieces in the solar system. They're unlike other planets. You don't have a rocky buildup or gases. They generally have highly elliptical orbits as they go around the sun. And most of them spend their time well beyond Neptune in a region known as the Kuiper Belt. The Kuiper Belt contains a ton of different objects, not just objects like Pluto, not just dwarf planets. Because Pluto has other planets or other dwarf planets even nearby, like Eris is beyond Pluto, but nearby. But we didn't call them planets, and they're bigger than Pluto, or at least Eris is. So why is Pluto a planet? And really, Pluto was just a planet because of the way it was discovered and when. Had it been discovered with all of these other objects, it would have never been considered a planet in the first place. The one thing I do want to point out is, of these dwarf planets, 4 of them reside beyond Neptune. Ceres, this one here in the middle, actually resides in the asteroid belt. It is basically the largest asteroid in the asteroid belt. It's considered a dwarf planet because it has the right shape, but it has a lot of stuff around it. So it's not a planet, and it's also very small.